Hello, everyone. Welcome to the course on Civil Engineering Materials. I'm your instructor, Chen Jiang. In this lesson, we will study Section 5.7, Deformation Properties of Concrete. Concrete is the most fundamental structural material in civil engineering. Its deformation behavior directly affects a structure's safety, durability, and serviceability, making it one of the key topics in the study of engineering materials. Before we begin, let's first look at the real-world engineering images on the screen. As you can see, some concrete structures have developed cracks and deformation, while some buildings are designed with expansion joints specifically to accommodate movement and deformation. All of these phenomena are closely related to the deformation characteristics of concrete. As a non-homogeneous composite material, concrete can deform even without external loads due to changes in temperature, moisture, and self-hardening. Under loading, it also exhibits elastic deformation, plastic deformation, and long-term creep deformation. If deformation is not properly controlled, it can lead to cracking, reduced load-bearing capacity, and even serious structural accidents. On the other hand, by understanding the laws governing deformation, engineers can minimize these risks through proper design and construction practices. Today, starting from practical engineering applications, we will uncover the fundamental principles behind the deformation behavior of concrete. The knowledge framework of this lesson is organized into 3 core sections. The first section focuses on deformation without external loading, covering the spontaneous deformation of concrete in the absence of external forces and the corresponding prevention and control measures. The second section examines deformation under loading, analyzing the behavior of concrete under both short-term and long-term loads. This is a key aspect of structural design and stress analysis. The third section discusses the main factors affecting concrete shrinkage, breaking down the causes of shrinkage and introducing methods for shrinkage reduction. These 3 modules progress from basic to advanced concepts, moving from theory to practical application, and provide a comprehensive coverage of the key examination points related to concrete deformation behavior. I hope you will follow the logic closely and build a solid understanding of the topic. Let's now move on to the first module, deformation without external loading. This type of deformation refers to the volume changes that occur in concrete without the action of external loads, caused instead by the material's own properties and environmental changes. It occurs throughout the entire life cycle of concrete from casting and hardening to long-term service and is one of the primary causes of early-age cracking. The main types include thermal deformation, moisture-related deformation, autogenous shrinkage, and chemical shrinkage. Thermal deformation results from the heat released during cement hydration and from changes in ambient temperature, causing expansion and contraction. Moisture-related deformation is caused by the evaporation or absorption of internal moisture, leading to shrinkage or swelling. Autogenous shrinkage occurs when cement hydration consumes internal water, resulting in spontaneous volume reduction. Because the tensile strength of concrete is much lower than its compressive strength, once the tensile stress generated by deformation exceeds the allowable limit, cracking will occur, greatly reducing the durability of the structure. For this reason, studying deformation without external loading is essential for crack prevention and deformation control. To deal with temperature and shrinkage-induced deformation, one of the most effective engineering measures is the use of expansion joints. By dividing the structure into sections, these joints help release deformation stresses and prevent cracking. The table shows the maximum spacing requirements for cast-in-place reinforced concrete expansion joints specified by design codes, classified according to structural type and service environment. For frame structures, the maximum spacing is 55 meters in indoor or underground conditions, but it is reduced to 35 meters in outdoor environments. For shear wall structures, the spacing is 45 meters indoors or underground and 30 meters outdoors. For thin-walled structures such as retaining walls and basements, the spacing is 30 meters indoors or underground, but only 20 meters in outdoor conditions. The allowable spacing is smaller in outdoor environments because exposure to sunlight and rapid temperature changes intensifies deformation. Differences among structural types are mainly determined by stiffness and restraint conditions. The greater the stiffness and the stronger the restraint, the smaller the required spacing between expansion joints. Strict compliance with these code requirements is fundamental to preventing cracking caused by deformation without external loading. The detailing of expansion joints directly affects their performance. Waterproof, thermal insulating, and highly elastic film materials such as asphalt, plastics, and rubber should be used. These materials can accommodate the expansion and contraction of concrete while also preventing rainwater and moisture from penetrating and corroding the internal reinforcement. When the joint opening is relatively wide, deformation joint cover plates made of materials such as galvanized steel sheets should be installed. The ceiling expansion joint cover shown in the figure is a typical example. The cover plate must be securely fixed while still allowing enough room for movement, so that the concrete can expand and contract freely without restraint. Whether in building walls, floor slabs, bridges, or retaining walls, the selection of materials and the construction quality of expansion joints must strictly comply with design standards, ensuring effective deformation relief as well as waterproofing, thermal insulation, and safe structural performance. After understanding deformation without external loading, we will now move on to the deformation of concrete under applied loads, namely deformation under loading. Deformation under short-term loading refers to the deformation of concrete subjected to short-term static loads, which mainly includes elastic deformation and plastic deformation. Elastic deformation is a reversible deformation that can fully recover after unloading and follows Hooke's law. Plastic deformation, on the other hand, is a permanent residual deformation that cannot recover after unloading. It results from the development of internal microcracks as well as slippage between aggregates and the cement paste. These characteristics are clearly reflected in the stress-strain curve of concrete. Under low levels of loading, elastic deformation dominates, while as the load increases, the proportion of plastic deformation gradually becomes greater. The key parameter used to evaluate the elastic deformation capacity of concrete is the modulus of elasticity. It represents the material's resistance to deformation. The higher the modulus of elasticity, the greater the stiffness of the structure. This parameter is essential in calculating member deflection and designing structural stiffness. The modulus of elasticity is mainly influenced by factors such as aggregate properties, the water-to-binder ratio, cement type, and curing conditions. High-quality aggregates and a low water-to-binder ratio can effectively increase the modulus of elasticity. Under long-term sustained loading, concrete exhibits a special type of time-dependent deformation known as creep. It refers to the phenomenon in which, under a constant load, deformation gradually increases over time. This is an important characteristic that distinguishes concrete from steel. The primary cause of creep lies in a viscous flow of the cement gel and slippage at the internal interfaces. Under sustained loading, the gel structure inside the concrete deforms gradually over time, ultimately resulting in continuous overall deformation of the concrete. Creep has both beneficial and adverse effects on structures. On the positive side, it can help redistribute internal stresses and relieve stress concentrations. On the negative side, it can increase member deflection, lead to excessive deformation, and cause pre-stress loss in pre-stressed concrete structures. Therefore, in engineering practice, It is important to make proper use of the beneficial effects of creep while minimizing its harmful impact through measures such as optimizing the concrete mix design, improving curing conditions, and controlling loading levels. Among all types of concrete deformation, shrinkage is the most common and the most widespread form of deformation without external loading. It is also the primary cause of early-age cracking. Shrinkage refers to the reduction in concrete volume in the absence of external forces, and it occurs throughout the entire service life of concrete. Earlier, we discussed the harmful effects of shrinkage and the use of expansion joints as a preventive measure. However, to control shrinkage at its source, it is essential to understand the key factors that influence it. Concrete shrinkage is affected by 5 major factors, which together determine both the magnitude and the rate of shrinkage development. The first factor is the amount and type of cement. Cement is the primary source of shrinkage, so the greater the cement content, the more significant the shrinkage. Ordinary Portland cement generally produces greater shrinkage than slag cement or fly ash cement. The second factor is the quantity and quality of aggregates. Since aggregates undergo very little shrinkage themselves and act as a restraining skeleton, a higher aggregate content and a higher aggregate modulus of elasticity can effectively reduce the overall shrinkage of concrete. The third factor is the water-to-binder ratio. A higher water-to-binder ratio creates more internal pores, leading to greater shrinkage. Therefore, reducing the water-to-binder ratio is an effective way to minimize shrinkage. The fourth factor is the use of admixtures. Proper use of water reducers and expansive agents can help reduce shrinkage, while improper dosage may instead increase it. The fifth factor is environmental conditions. High temperatures, low humidity, and strong winds accelerate moisture evaporation and increase drying shrinkage, whereas adequate moisture curing can significantly reduce shrinkage. These 5 factors are closely interconnected, so in engineering practice, they must be controlled in a comprehensive and coordinated manner. Based on the factors affecting shrinkage, shrinkage reduction measures can be implemented throughout the entire construction process to prevent cracking in concrete structures. In terms of materials, low shrinkage cement should be selected and its dosage properly controlled, while aggregates with high strength and a high modulus of elasticity should be preferred. For mix design, the water-to-binder ratio should be strictly reduced, and mineral admixtures such as fly ash and ground slag powder can be used to partially replace cement, thereby reducing shrinkage caused by cement hydration. With regard to chemical admixtures, high-performance water reducers and expansive agents should be used appropriately to regulate the hydration process and compensate for shrinkage. During construction, proper compaction must be ensured to minimize internal voids within the concrete. Curing is especially critical. After casting, the concrete should be promptly covered and kept moist, and the curing period should be extended whenever possible to slow moisture evaporation. In addition, by combining measures such as properly designed expansion joints and reasonable reinforcement detailing, multiple control strategies can work together to minimize shrinkage and ensure the long-term durability of the structure. This lesson is focused on the deformation behavior of concrete and covered 3 core areas. First, we examined deformation without external loading, including its types, hazards, and the preventive role of expansion joints. Second, we analyzed deformation under loading, covering short-term elastic and plastic deformation, as well as the long-term behavior of creep. Third, we discussed the key factors influencing concrete shrinkage and corresponding methods for shrinkage reduction. The deformation behavior of concrete is a fundamental topic in civil engineering materials. It is closely connected to every stage of structural design, construction, and maintenance. Whether it is the design of expansion joints, optimization of mixed proportions, or control of pre-stress loss, all rely on the theoretical foundations covered in this lesson. I hope you will keep in mind the essential principles of concrete deformation, understand its relationship with structural safety and durability, and, in your future studies and professional practice, apply this knowledge flexibly to solve real engineering problems, effectively control concrete deformation, and contribute to the creation of safe and durable civil engineering structures. That's all for today's lesson. Thank you, everyone.